when we operate a transistor and we design it right, then we can basically ignore temperature, right? And so that's why on the saturated switch. So what happens to beta? What relationships does beta and temperature have? Come on, guys. Yeah, so temperature goes up, beta goes up. And beta goes up, what current goes up? Huh? IC goes up. Okay, if IC goes up, then the transistor is going to get a little hotter, right? You understand? Because even if beta goes up, the transistor drops less voltage, but remember, current is more predominant in power because it's I square R. So even though the R of the transistor drops a little bit, current varies by the square, right? So current goes up, the causes the transistor to get hotter and then causes beta to go up, which causes current to go up, and we refer to this as thermal runaway. I was reading an article about a new type of transistor we call a insulated gate bipolar transistor, and when they first started developing it, that was the problem they had, was that it was going into thermal runaway. And now we understand what that is, right? So, but when we get operating, so thermal, if we design a transistor switch right, then we basically don't have to worry about thermal runaway because we use the minimum beta and the collector current can't go up because it's saturated. Y'all understand what I'm saying? Okay, because our load is up here in the collector. And once that load drops the applied voltage, it cannot drop any more voltage. The problem we have is that if we don't make it drop the applied voltage, which means we're operating in the active region. So I think we were dropping right around, I can't remember, what was we setting up? So the circuit I have is, guys, the circuit that we have up here is we have this circuit right here. So we're using a bias that we call base bias. Okay. But we're operating this in the act. I don't know why it's changing colors on me. So I'm using the pen, and the color I'm selecting is black. So we had, I can't remember. Let's set it back up again. Let's turn it on, and we're measuring about 3 volts. So connected to the and I need another meter. That's okay. I'll just move it over. So my VCC supply voltage is setting at 6 volts. Right here I got 3, so I got to drop in 3.7. So we're operating in the active region, right? And what did we do the other night? I got this device right here called a soldering iron, and what happened? When I heated it up, the voltage drop across the transistor went down. So if the voltage drop across the transistor is going down, then the voltage drop across this 150 ohm resistor is going up, right? So we were seeing the thermal effects of the bipolar transistor. Are we okay? So I'm gonna plug in my soldering iron. So when we operate this in the active region, then the transistor could very easily go into thermal runaway. So one day I might have 3 volts out, and then it gets cold outside, right? And then I might have 5 volts out. Then it gets real hot outside. Then I might have 2 volts out. and we can't handle that, or we can't do that with especially amplifier circuits. So we okay? So this is what we call base bias. So what we do on base bias, we use a single power supply, and then we have a base resistor that's setting the base current. And we choose this resistor to size this base current depending on where we want to set this guy right there. So it's not very hard to design. So I come over here and I say, okay, I want this guy here to drop 3 volts. 3 volts, I would calculate the collector current. I would come up here and divide it by the typical beta of the transistor. Then I would come over here and subtract 7/10 of a volt, and I would size that base resistor to do that. And then I choose the standard value and play around with it, right? And that's transistor design. So this is PNP. These are NPN base bias. This would be PNP base bias. Here we have a minus VCC. And this right here is base bias, but notice we swap things around. We're taking the collector and hooking it to common, and then we're hooking up the emitter to the plus DEE voltage. Can y'all see that? Are you okay? Saturated switch, this is probably the most popular circuit. We come up here, we replace this resistor with our load, whatever we want to turn on, an LED or a light bulb or whatever, and then we take it from there, right? Everybody okay? Trying to operate it as an amplifier is going to give us problems. So they started messing around. They came up with something called collector bias. Now, collector bias, can you see what's happening here? So we set up our bias basically the same way. We want this to be sitting at 3 volts. Now it's working great. It's going to be sitting at 3 volts. Are we okay? And then I would size this resistor to drop 2.7. So a while ago we sized it to drop 4.7 volts, right? Now we're going to drop, if we're going to set this at 3 volts, I would calculate my collector current, so this would be 6 volts, and then I'd say, okay, what current do I want? Let's say we want 1 milliamp. Then right here, I would set this for a 3K resistor. So a 6K would drop all of it. A 3K would do what? Drop 1/2. That would set this at 3 volts right there. This resistor right here would drop 2 point this. I would come over here and use what we call typical beta, and then we're going to have to play around with that, right? Typical beta on a 2N3904, which is the one we're going to deal with, typical beta is 100. So I could take the 1 milliamp, I could divide that by 100, then that would give me my base current that would be required. What would that give me? $10 microamps. So it'd be 10 microamps, and then I would choose a resistor, so RB would be equal to 2.3, Rich. 2.3 divided by 10 micro, and then we'd go from there. That's okay. Okay, are we okay? And then, of course, I would choose a standard resistor, and I would play around with it because we're using typical beta instead of actual beta, right? Are we okay? All right, so what happens if temperature goes up? Well, if temperature goes up, collector current tries to go up. If the collector current tries to go up, this resistor right here drops more voltage. If that resistor tries to drop more voltage, let's say it drops down to 2.7. Well, this voltage right here is going to drop down, which is going to cause base current to drop down, which is going to cause collector current to go back down. Y'all see that? Y'all understand how that works? Can we see that again? Okay, so let's say this guy here drops 3 volts. Now, this 10 microamps is depending on this right here being 3 volts. This is going to drop 7/10 of a volt, less of whatever that is. So that right here is depending on this right here to be at what? This right here to be at 1 milliamp. Base current is setting the 1 milliamp. If base current goes down, IC goes down. If base current goes up, IC goes up. Y'all understand that? Ain't just neat? So let's say this current tries to go up to 1.2 milliamps. Well, if it goes up to 1.2 milliamps, this 3K is going to drop less voltage. We don't have to calculate it. If it drops less voltage, that means there's going to be less voltage drop across this resistor right here. If that voltage drops less, that means base current is going to go down. If base current goes down, collector current is going to do what? Go down. So if the collector current tries to go up due to temperature, the base current is going to go down to keep it at the same spot. And this is called collector bias. And the purpose of collector bias is to prevent thermal runaway. Collector bias is really nice, but what it does, it affects the gain of the circuit. So if I come in here and put an AC signal in here, which we can't do right now because we'd have to have a resistor, then the gain of the circuit would be, we could get as much gain out of this circuit as we can with the next bias. But this guy would go into thermal runaway. Can y'all see why? Everybody okay? So where else can we put a resistor at? So these are different examples of, this is emitter bias. And we got all types of options here. And it works on exactly the same principle. So if this guy drops 1 volt, let's say it drops 1 volt, let's say this guy right here drops 0.5 volts. Now, this 3 volts and this 0.5 volts is set by this collector current. This voltage right here is going to be the difference, right? You understand? So let's say I have this set at 0.7 of a volt, and this right here is setting at, what was this, 6 volts? This is setting at 5.3 volts. Okay. This point right here would actually be, this would be 5.3. This relative to common, if I took a meter and put it right there, so this would be 0.7 of a volt. This would be 0.5 of a volt. This right here would be what? If this is 0.5 of a volt, what would that be right there? It's going to be sitting at 1.2 volts. I understand we're working back through here backwards. If this is 0.5 of a volt, how much does this guy right here drop? 0.7. So that means relative to common, the base is going to measure what now? 1.2 volts. And then this resistor right here would be dropping the rest. What would that be? 6 minus 1.2 is going to be what? 5.8. No, 4.8. Okay. So what happens if the current goes up? It tries to go up. Well, if the current tries to go up, this resistor here is going to try to drop more voltage. If it tries to drop more voltage, that's going to try to cause this guy, if this drops more voltage, this voltage right here is going to have to do what? Well, it's going to try to drop more. This guy right here, if this goes up right here, understand, this guy right here is trying to maintain 0.7. This guy right here is trying to maintain its voltage. So what happens is this right here, this voltage right here is going to try to go down. But it can't go down because it's anchored at what? 0.7 of a volt, right? So what's going to happen is if this guy drops more voltage, this guy here is going to do what? This is the important one. If this guy drops more voltage, what's this guy right here going to do? According to Kirchhoff's law, this right here is set at 0.7 of a volt. Right? You understand? If this guy drops more voltage, this guy right here is going to do what? Drop what? Less. This guy right here is setting the base current. So if that guy drops less, what's going to happen to the base current? Huh? It's going to go down, which is going to cause collector current to do what? Huh? So collector current is equal to this. So our formula is beta is equal to IC over IB. So IC is equal to IB times beta. So what's happening is if IC tries to go up, it tries to make this resistor drop more voltage. If this resistor drops more voltage, then what happens to the base current? It goes down. What happens to beta? Huh? Well, it's not going to go down. It's going to do this. Y'all understand? So beta tries to go up. IC tries to go up. IC tries to go up, but it can't go up because this resistor over here is going to try to drop the same. So this resistor right here, according to Kirchhoff's law, this is 0.7, this is 7, this is 0.7. It's got to add up, right? You understand? So that means the voltage drop of this resistor had to go down. If the voltage drop on this resistor goes down, base current goes down. If base current goes down, IC goes down. But IC didn't. It's going to drop back to where it was supposed to be, right? You understand that? So what happens is IC is going up, IB is going down, and what's beta doing? What's beta doing? What's beta doing? Saying the same. So IC tries to go down, if IC tries to go down, IB goes up, right? You understand? Y'all understand? So what happens to beta, even with temperature? So if temperature goes down, what happens to beta? Stays the same. If temperature goes up, what happens to beta? Stays the same. So, and what's changing the beta of the transistor? So if temperature goes up, but we still have a problem in that this voltage right here changes, which means the gain of the amplifier changes. But here we're not dealing with collector current, we're dealing with the base current, right? You understand? So the gain of the circuit, y'all know what gain is? What's gain? What's gain? Any gain. So if I came up and I got a raise, now I'm making $6 an hour, and the boss says I'm gonna give you $7 an hour. What would be my gain? I wouldn't say $1. What would be my gain? You know, percentage. So here when they tell us they don't give us money. They say, well, we're gonna give you a 2% raise. Well, that 2% is just like beta, right? You understand? So how do we calculate that? How do we calculate that? I mean, how do we figure this? Well, gain is always out divided by what? N. If I want to know voltage gain, then I do what? By the way, in formulas, we represent gain with the letter A. Because G is already given up for conductance, right? And then I would say V out divided by what? The N. Power gain would be what? Yeah, AP would be equal to P out divided by P in. Current gain would be what? AI would be what? I out over I in. Now, which one of these is the most important? Which gain is the most important? Huh? Huh? This gives people work. This is work. This is how much work I'm getting. So when Alabama Power When they send you a bill every month, they don't send you a voltage bill. That's not what's important to them. They don't send you a current bill. Of course, those are important. You can't have power without current, and you can't have power without voltage. But they don't send you a voltage bill. They don't send you a current bill. They send you what? Power. Why power? Why don't they send you a voltage bill? Be very complicated. One thing, you got two powers. Their voltages are all over the place, right? Power is work. So any formula that we do, when I'm trying to get a transistor amplifier, what am I trying to get? I'm trying to get power gain. That's the name of the game. So the most popular bias used in transistor amplifiers is what we call the voltage divider bias. What we do is we clamp the base with a voltage divider. So this voltage is clamped. It cannot move. So on the emitter bias, so it's a form of emitter bias, but what we do is we clamp the voltage on the base with a voltage. And then if this voltage right here if that voltage tries to go up, it can't. Because if it tried to go up, it would try to change that 7/10 of a volt, right? Y'all see what I'm talking about? So let's say we clamp this right here at 3 volts. Then right here I would have 2.3 volts. Well, what happens if collector current tries to go up? Well, this voltage drop right here would try to go up, but it can't go up because the base is clamped at 3 volts. So this resistor right here cannot change its voltage drop. So if collector current tried to go up, it can't because it would change the base voltage. It would try to make the base voltage go down, but the base voltage can't go down, right? Because it's clamped at what? This guy right here, it'll operate all over the place. This right here is neat, and we designed this without beta. We figure out what goes on without beta. And why don't we want to use beta? Because it what? Why don't we want to use beta when we calculate stuff? Because it's all over the place. Now we do use it a little bit, but we're going to use it for an approximation. Okay, guys. So how would you think we would figure out what VB would be for this thing? What's VB? That's if I come over here and took a voltmeter and put it right there. Now, what you got to understand is we'll look at this in a second, and we'll see the beta of the circuit. But when we calculate this, we ignore this path right here, and we'll talk about why. So all this is a series circuit. Where did y'all learn series circuits at? DC. Now VB is going to equal to the voltage drop across which resistor? Huh? Well, no, but it's not going to be VR1 plus VR2. VB look, here's this and here's this. It's going to be equal to the voltage drop across R2. So all I got to do is calculate the voltage drop across R2, and I've got VB. So it's going to be equal to VR2. By the way, these are generic numbers, so when we play around, this is what we're going to call these resistors. We're going to call the collector resistor what? RC. The emitter resistor, we're going to call it RE. Then this resistor we call R1, and the bottom resistor we call R2. Now, in an actual circuit, what could it be? Yeah, you're not going to see an RC. You might see an R53, right? You understand? Okay, so somebody tell me how do I calculate VRB? VB, which is the voltage drop across R2. Get your calculators out and do it. Voltage divider formula is the easiest to use here. Y'all know the voltage divider formula. So what's the voltage divider formula? It's the applied voltage, 20, times the ratio of these two resistors, which would be 10K divided by 100K, which would be 1/10, because the K is going to calculate, this 2 zeros are going to drop about 1/10. Okay, so that means this is going to drop 1/10 of the voltage. So it should be what? So I've got this in my head. Voltage divider formula is cool, right? So what we got? I know what it is. Y'all probably know what it is. What is it? Huh? 1/10 of 20 volts is 2 volts. So this guy right here is going to drop 2 volts. We'll hook this up on electronic workbench in a minute. So what laws are we using? Voltage divider formula, where'd y'all learn that at? Should have learned it in DC. If they're not teaching this in DC, because we use this. Why? Because most of the time we're only dealing with 2 resistors. Now, what you do in DC, you calculate RT, you divide it by this, you come up and get IT, you do that, you multiply it by this. There's no need to do that because the voltage it drops is relative to the other resistors in the circuit. The voltage divider formula, you do that without calculating I, right? You understand? No, the actual formula would be VB, but I took some shortcuts because I know math. Okay, so I know 10K over 100K. What do I have on the top? Well, I got 2 Ks. What do the Ks do? Cancel. I got a 0 here and a 0 there. What does that do? That cancels. So that's 1/10. So I knew this without even picking up my calculator. I knew that was 2 volts without picking up a calculator. Now, of course, this is easy, but you find out most of the time RT on a 2 resistor circuit, a lot of times you can do RT in your what? In your head. Now, sometimes it's going to be, if this was, if this was 470 and this was 47 down here, it would be the same ratio, but now you're going to have to do math, right? You probably have to get your calculator. Okay, so that's 2 volts. Okay. What would be the voltage drop across RE? First of all, is it forward biased? The emitter is pointing toward ground. It's a PNP. I'm sorry, it's an NPN. So I need an N relative to that P. This guy right here is sitting right here at common, which is 0 volts. So this guy is pointing toward circuit common. This guy has a positive 2 volts. There's ENP. This guy's reverse bias. There it is right there. That's a big 20 volts up there. The transistor's forward bias is going to cut on. So if this guy here is forward bias, that means this guy right here is going to drop how much? 0.7 of a volt. According to Kirchhoff's law, the sums of the voltage drops in this little loop right here have got to equal to 2 volts. So if this guy here drops 0.7 of a volt, how much would that be left across RE? So VRE is going to be equal to 1.3 volts. What law did we just use? Kirchhoff's law. Okay. Now, I know 2 things about RE. What 2 things do I know about RE? I know the voltage across RE, and I know the size of RE. So what can I calculate? I can calculate IE. So I equals to 1.3 divided by 1K. So IE equals to 1.3 milliamps. So that means I got 1.3 milliamps flowing up and sitting right there. About 1% flows that way. 99% goes that way. So we're going to assume, even though it's not true, we're going to assume IE and IC are equal to each other. Are they equal to each other? No, but they're so dang close. So if I know IE, I'm going to use that IE. Now I know IC. If I know IC, what do I know now? This is a series circuit. I don't know the resistance of the transistor, but by George, I do know the resistance of that resistor right there, right? So I can calculate VRC. Is this complicated so far? Good gracious, all we're doing is what? This is easier than a lot of the circuits you did in what? DC. So VRC is going to be equal to IE, which is 1.3 milli, times 10K. So what's it going to drop? It's going to drop a lot. Yeah, it's going to drop 13 volts. So it's going to drop 13 volts. So we've got this thing operating toward cutoff. We call this, so this is VRE is 13 volts. Okay, so what would be our voltage collector to emitter? Kirchhoff's law, guys. 13 volts here, watt 1.3 volts there. It's a series circuit. Kirchhoff says the sum of the voltage drops down this series circuit has to be equal. So we're operating pretty close to saturation. We need to change some resistors, but these are easy to calculate. So what's voltage collector to emitter? So that's going to be equal to 20 minus 13 minus 1.3. So voltage collector to emitter would be equal to what? Have I lost anybody? I mean, this is just what? This is DC. But this is an amplifier. So what's our voltage collector to emitter? Are we in saturation? Are we in cutoff? Are we in the active region? Huh? Active. Why? Because it's greater than 1 and less than DCC. We would like for it to be around 10 volts, but this is okay. What would VC be? So VB is going to be equal to 2 volts. VC is going to be equal to what? So VC, how do we measure VC? So this is what we measure. So normally when we make these measurements, we don't measure VCE. We usually calculate VCE. We don't like to get 2 meter leads into a transistor because the leads are usually so close on the transistor. So what we do is we come up here, we make 3 measurements. We make one measurement right here. We make another measurement right here. And then we make another measurement right here. Oh, I'm sorry, this is the same thing. We can make another measurement right here, I'm sorry. So what would B be equal to? So this guy right here is VB. It's going to be equal to 2 volts. Okay. Now VE is going to be equal to the voltage drop across this resistor. That's going to be 1.3 volts. What would VC equal to? Y'all math guys. Somebody help me. So this is usually the way we measure the transistor. We don't like to get 2 meter leads into an electronic circuit if we can help it. Sometimes we have to do it. So usually your meter measurements are relative to the common of the circuit. And a lot of times they'll have you a stop, or there'll be a capacitor, or there'll be something where you can take an alligator clip and clip it onto the common. And then you go around probing with one lead. It makes it a lot safer, not only on preventing shorts, but also from getting you shocked, right? And you get into some of these power amps, you're talking about 160 volts across the plus and minus supply. And by George, that'll kill you. And that's DC too. That's not AC, that's DC. What makes DC dangerous is that you get into a high voltage, you get enough current, it's going to grab you, it's going to hold on to you. The problem with the AC, if it flows through your heart, then your heart's going to try to beat at the rate of the AC. And your heart can't beat 60 times a second. Mine beats around 50, 59 beats a minute, which is pretty standard for some people. When I was laid up in the hospital, I was around 90. Your heart's beat real fast when you're trying to heal yourself, don't it? Okay, guys, VC. So we know VB is equal to 2 volts. We know that VE is equal to 1.3 volts. So what's VC equal to? So what'd you say? Well, so what we do to we can do it two ways. We can add, but I don't know this one. We don't measure this one. Normally we measure this, this, and this. So normally DC would be equal to VCC minus VRC. That's Kirchhoff's law. So what we're doing is only difference between here and here is the voltage drop between these two resistors, right? Or these devices. So what should we expect VCC to be? So VC would be equal to 20 volts minus, what was the voltage drop across RC? 13. Now, if I need this, I can calculate voltage collector to emitter. It gives you the formula. Voltage collector to emitter. So what I would do is I would take my voltage on my collector, which is 7 volts. I would subtract from that my voltage on my emitter. So this tells you the formula right there, right? Collector to emitter. I would subtract from that my voltage on my emitter, which is 1.2 volts. I mean, what? 1.3 volts. And that would give me my voltage collector to emitter, which we usually don't measure. Y'all understand why? Y'all seen the transistor? Well, not yet. I passed one around. Now see how close those little leads are together? And a meter lead will not fit down between two of those things. So you're up here trying to look at your meter, and you got 2 meter leads out there. What's the odds of one of those flipping? Pretty dang high. You touch 2 meter leads, you touch 2 of those leads together, you could pop that transistor just like that. One is good, not good enough, but you could be. And normally we try not to measure on the transistor. We try to measure back here on these resistors. So if I want to measure VB, I try to get on this metal lead right here. If I want to measure VC, I get on this guy right here, right? And if I want to measure VE, I measure it on that resistor right there. And I try not to measure on the transistor. And we don't have to. We got plenty of nice metal on our resistors trying to do that. Guys, this guy here will have a gain of 10. We're going to bring our AC in right here. And what we're going to do, we bring it in with a capacitor. What's one of the things we said about capacitors? What do they do with DC and AC? Anybody remember? They block DC and they pass AC. So what that's going to do, it's going to let our input signal come in, and it's going to subtract from or add to that base voltage right there. So if the base voltage goes up, then the transistor is going to cut on more. If the base voltage goes down, then the transistor is going to cut off, move toward cut off. Right? You understand? So let's say we come over here. Let me erase most of this math. But what did we do on that? Where did you learn all that stuff at? Where did y'all learn all that stuff at? What laws did we use? Ohm's and Kirchhoff's. And the voltage divider formula. But that wasn't a law, that was a formula. Okay, so let's look at our, so what voltages do we have? So this guy right here is 2 volts. VE was what? 1.3. Okay, and this guy up here was dropping 13 volts, right? VC was setting at what? So VC was equal to what? Huh? Okay. Okay. So let's bring a signal into this thing. Over here, I'm gonna put we'll just put a sine wave on this, and let's do 1 volt peak to peak. So that means it's going to go 500 millivolts up, and it's going 500 millivolts down. And we'll put this on there. This is so neat. So let's say it's going up right here. So if this goes up, this guy right here is going to go up to 2.5 volts because that'll be, they're adding, right? You understand? This guy right here is going to go up to what? If this goes up to 2.5 volts, now let's talk about bias. Bias, this guy can't move. So I could heat this sucker up all day long with bias, and this the voltage drop across this resistor right here wouldn't change. Because if the voltage drop across this resistor tried to go up, and I have this set at clamped at 2 volts, it can't go up, right? You understand? Because that junction's got to drop 0.7 of a volt. So that means this guy here will not go into thermal runaway. But what we're doing here is we're actually changing the input signal is changing the base voltage. Can that happen? Sure. So 500 millivolts in, it means this goes up to 2.5 volts. If that goes up to 2.5 volts, what happens over here? Huh? 0.7 of a volt, guys. 0.7 of a volt. It was setting at 1.3. What's it going to do? It's got to go up, right? So it's going to be 2.5 minus 0.7. What's it going to go to? What's that? Okay, 1.8. If it goes to 1.8, my emitter current drops down to 1.8 milliamps. If it drops down to 1.0 milliamps, and this guy up here, instead of, if it drops down to 1. Is that right? No. Oh, it's going up, right. It's going to go up to 1.8 milliamps, right? So now this guy right here is going to drop 18 volts. If it drops 18 volts, this guy right here is going to drop down to 4. So the input's doing this, but this is 500 milliamps. This was setting at what? What did we originally have it setting at? So let's go back and get these voltage measurements before, because what we're trying to see is how we can get voltage gain out of this amplifier. And it's real easy to calculate. So let's get back where it was setting. So where was we at? I know we went past our break, but we need to. This is at what? 2. This is at what? 1.3. 1.3, Rich. My IE is equal to what? 1.3 milliamps, right? Are we okay? Okay. This guy right here is dropping 13 volts. So it leaves us with 7 volts right there. Are we okay? Okay. So the input goes up, 500 millivolts comes in. We let it come in through this. This don't let the 2 volts get out, but this lets the what? This lets the AC get in. So one of the rules of thumbs of AC of capacitors, if we choose them right, then they pass AC and block DC. So this comes in right here. These guys are considered to be series aiding, which means this is 500. This guy right here is going to go up to 2.5. If that goes up to 2.5, then this guy over here is no longer 1.3. It's going to go up to 1.8. Right? Okay. If it goes up to 1.8, it's 1K. That means IE goes up to 1.8 milliamps. Okay, if that goes up to 1.8 milliamps, that means this right here would drop 18 volts. Which means this guy right here would drop 1.18, but this guy right here would drop down. No, something's going on here. We can't do this. Dang it. Y'all know why? Okay. If this drops 18 volts, yeah, I believe we can. So if this is 18 volts, this right here would drop down to what? 2. So while we were sitting here, is we were originally setting up here at 7 volts. What we did now is we just dropped down to what? 2 volts. So 500 millivolts in, 2 volts out. See that? 500 millivolts in, 2 volt change out. Now, of course, on the input, we're going positive. The output's going negative. It's not going to go negative, but it's moving negative, right? Because 0 is down here. Okay, so we come back up. We go back to 2 volts. We would be right here. Now the input goes to minus 500 volts, 500 millivolts. That means this right here would drop down to 1.5 volts, right? And everything in between, which would cause cause the voltage drop across this resistor would be 1.5 minus 0.7. That's going to give me what? Huh? Yeah, 800 millivolts. So that means my current is going to drop down to what? So IE would be equal to 800 millivolts divided by 1K. What's that going to give me? 100 microamps, right? I'm sorry, 800 microamps. 800 microamps? Okay, 800 microamps. Okay, so that means this guy up here now is going to drop what? It's going to drop 8 volts. Now we have 13 volts right here. So that means this output, I'm not going to be able to do that. It's going to go 5 volts up. It's going to go up to 13 volts. So as my input is changing right here, 1 volt peak to peak, this output out here is changing 10 volts peak to peak. Now, of course, if we bring it through that capacitor, so over here what we have is we have DC, we have AC riding on top of DC, right? You understand that? As soon as I pass it through that capacitor, what I'd get over here is I'd get AC. Over here, I'm getting 10 volts peak to peak out. And over here, I'm putting 1 volt peak to peak in. We got a voltage gain of 10. So what the input signal, we're going to bring the input signal here. What's that input signal going to do? It's going to change this voltage. Then it's going to come over here. It's going to cause the voltage across this thing to change. Right? You understand? Which is going to cause the voltage drop across here to change. Which is going to cause my output voltage to change proportionally. So did we get a voltage gain out of this? Sure. Would we get a current gain out of this? We could. Well, it depends on what we hook this thing up to. You know, if I hook this up to a 100 ohm resistor, we're going to get a lot of current gain. If I hook it up to 1 mega ohm resistor, we're not going to get any current gain. So it all depends on what load this amplifier is driving. And by the way, the load actually affects the gain. If I put a load out here, what would you expect the gain to do? Would you expect it to go up or go down? So when I said a gain of 10, I did that in my head. But if you put a load out there, would you expect the gain of the circuit to go up or go down? Huh? Down, because we're getting, now the amplifier is having to provide a current, right? And anytime we load something down that's not regulated, output's going to go down. So what we'll start off with we'll start off with looking at these things unloaded. And it's really easy to calculate the gain when it's unloaded. Just take this resistor and divide it by that resistor, 10K divided by, and that gave me a what? Gain of 10. And I told you we had a gain of what? 10. 10 volt peak to peak out, 1 volt peak to peak in. Are we going to get power gain? Odds are we will. Because if I get a voltage gain, I'll get a power gain. Even if the resistance over here was the same, then we would get a power gain. And we'll look at that. Y'all take a break. And I'll do this on the electronic workbench, and we'll see this thing work. And we'll see later on how to really get some gain out of this guy. Here we're operating towards saturation. Where's it at? Ah, dang, I must have cut it off. Prepared. And we'll talk about later on. So we wouldn't use a real tiny, and we're using polarized capacitors. You have to put them in there right. And right now we'll take our output off over here. So we're going to hook up something that we can hook up to. Electronic workbench, let us get by with this. It don't like open stuff. Don't like open elements. But we'll see. Then I'll put a capacitor over here. Now what we're going to do here is flip this guy here around. So to flip it on here, you hit Control R, and then you can flip them any way you want to. And then what we're going to do is we're going to come over here and use a function generator. And we got it set to sine wave. And let's see, we're going to put a common. Oops, wrong thing, Rich. We'll drag a common right here to the center. And we'll have to look. I can't remember this. It says 10 volts. I think this is RMS. I'm not sure. We'll put it back here on 1 volt. And we'll take this and connect it to our input. We'll put let's go ahead and put a load resistor out here, but I'm going to put one. I'm going to put a real big one so we can measure across it. So I'll put like a 1 meg out here. That way it won't affect our gain that much right now while we're trying to see these things. And then we'll come up here and set up our, I didn't need that dot there, but it's okay. And then I'll put a common on our output. And then we'll pull a voltmeter down, and we'll close up all this stuff. Come in here and change the values. This guy up here was supposed to be a what? Y'all remember? Wasn't it a 10K? Or no, it was 100K. We'll go back and look at it to make sure. And this down here was so 100K, 10K, 10K, and 1K. Now this is a very poorly designed amplifier, but it's good enough for demonstration. So 1K down here we have 10K, and up here we have 10K. And then down here I have 1K. And you can label these, by the way, so you can come up here and if you double click right on the component itself, there's label. So I can label this R1, and then I can label this R2, and then we call this guy here what? We call this RC, and we call this guy RE. And then we'll call this guy right here RL. Okay. Here's our meters right here. I'm going to come down here and break down my voltmeter. And so we're going to take the black lead, which they call negative, and we're going to hook this up to common. And then we're going to probe with this other meter. And this shows us what we're measuring. So we got 1 volt. We got, let's go ahead and put it up to some hertz. So, because we don't, the capacitor is really going to come into play. We don't want those yet. So kilohertz, put a sine wave into it, and I'll show you what audio looks like. So normally when you want to troubleshoot an amplifier, you'd like to have a function generator so you can put a known signal in so you know the signal is supposed to come out. So let's check this out. We'll turn it on if I can get the simulation to come on. I have to figure out where I did a while ago. Oh, there's another place. There it is right there. So we'll turn the simulation on. And it will just come back and measure. So when we measure voltage on the base, we should expect, if this thing does according to our calculations, here we should measure 2 volts. Here we should measure 1.3 volts. Here we should measure, what was that? Okay. All right. So let's see. So we'll turn the simulation on, and we'll come up here, and we would measure this. Got my meter on, make sure my meter is on DC, volts DC. And we'll come up here and look right here. Oops, if I can get it to connect. Turn the simulation on. Let's. I don't know if I can set this to 1 millivolt. Let me disconnect this for right now. Measure 1.73 volts, which is 300 millivolts less than. Wait, I know what we're doing. Wait a second. So we're going to go to a Motorola National 3904, right? Still measuring 1.7. Huh? Okay. I just took for granted. 1.8? Oh, okay. Y'all didn't call me on that one. Oh, dang, wrong thing, guys. Let's go back and, because I came up with, it don't mean I'm right. I've been wrong before. 1.8 would actually be better because that would make it a lot closer. So we would calculate it how? Yeah, VB calculated should be equal to 20 times 10K divided by 100K. Oh, thank you. Duh. Why didn't you bring it up a while ago? Because I'm the teacher and you're scared of me, huh? Okay, so it's supposed to be what? So let's go back and redo these real quick. 1.8, it's not even changed the game, by the way. 1.8, it's just we can't put 1 volt peak to peak in anymore. And I don't know if I can do it. We might have to change this resistor right here. So it'd be 1.8 volts. This down here would be what? 1.1 volt. That would be 1.1 milliamp. So this guy right here would drop 11 volts, so right here we should measure 9 volts, right? Everybody okay? Is that right? Did I screw up again? We okay? Thanks, Drew. So 1.5, 1.75, that's pretty good. And we calculated what? 1.8. Okay. Now this guy, we should expect it to drop around 0.7 of a volt. If I can disconnect, it's probably easier to disconnect it over here. Or at least I thought it would be. There we go. And then measure right here. Measures about 1.1 volt, 1.08 volt. And then measure right here. It's measuring 9 volts. Is that right? Is that what I came up with? Okay. Now this is bias. So what we're going to do now is put the signal into it. And notice I'm putting AC into this. So what's happening is right now, and if I look at the output with an oscilloscope, so what's so neat about this is, so what I'm doing is I'm putting 1 volt in, and I'd have to go see what that is. And we know this thing's getting a gain of 10, so that means we should be getting 10 volt peak fig out. And it's going to be 180 degrees out of phase, because when the input goes up, the transistor turns on more, which causes its opposition to go down. We're taking the output across the transistor. Now in audio, that means nothing, because in audio, what two things does your ears hear? What two things? It hears frequency, so I'm not changing the frequency, and it hears power, right? Or hears the actual voltage change, but it's actually power you're hearing. So I'm not changing the amount of output voltage, which is going to set the power. That and the current's going to set the power, and I'm not changing the frequency. All I got to do is make sure that if I in stereo, if I shift my left by 180 degrees, I got to shift my right channel by 180 degrees. If I don't shift them, then the two channels would be out of phase. We don't want the two channels to be out of phase with each other. But as far as in audio, if you have a phase shift through your amplifier, that's no big deal as long as it's the same in both your left and right channels, right? I just made my goal sitting here. So we know this guy over here is going to be 180 degrees out of phase. But when I look at and it's going to be riding on top of my original bias, so it's going to be riding above a certain voltage. And we got to be real careful, because if this is 0 volts, if I ever let my gain go and drop past 0, we can't go by 0. So what happens if we try to overdrive this? We get clipping on the output. If we try to go all the way up to 20 volts, the transistor is going to cut off and it will clip the top. If we try to drop down below 0, it'll clip the bottom because the transistor is saturating. Once the transistor drops 0 volts, it can't drop anymore, right? You understand that, or less than a volt. So we got to be real careful on what size signal we put on this, and we'll try to show you all that too. So why don't we see the AC? Well, I got my meter on DC. And what's my meter going to do? What's the average DC value of an AC signal? Well, it's not 0, it's down the center. This is 0 as far as my AC signals go. So my AC signal, my meter don't see that. So on an amplifier, you can measure the bias voltage even if it's active. Because even if it's sound, and it's all over the place, so sound looks like this, it's all over the place, but still it's going to average down the center. For every one going up here, we have the other one coming down here, right? You understand? So you can measure the bias voltage with it playing loud open. And we can tell a lot about the bias voltage, because if the bias voltage is wrong, everything's going to be wrong. Because what does bias do? It sets the operating characteristics of the amplifier. If the bias is wrong, then something's going on in the circuit. But if I come up here and look at this with an oscilloscope, So this is my oscilloscope. It's a dual, and it has this electronic workbench has a real problem synchronizing, so it's going to be hard for us to trigger this, I don't think. So here's my ground lead up at the top. So I'm going to connect a ground to my a common to my oscilloscope. By the way, this guy uses ground symbol for everything, so and it connects right here. And then channel 1, we'll come up here and hook channel 1 up, and we'll hook it up to the input right there and see if it. Okay, so that's it. So we need to change the position. Okay, so there's the position. What else do I need to do? Need to set my volt per yeah, looks like my AC signals has got a DC offset on it. Let's look and see if it does. No, it don't. I don't know what's going on, guys. Going to put less volts per division in. Right now I got 20 volts per division. Looks like I'm gonna have to keep shifting my my ground reference. For some reason I've got an offset on this, but that's okay. Okay, so now I'm seeing a solid bar. What does it mean about my oscilloscope? It means I'm going too slow, right? So I'm going to decrease the time per division. Okay, so there's our AC coming in. And this guy here don't want to trigger, but we can get a pretty good idea what this thing is. So it looks like it's RMS because we're getting we have it on 1 volt per division. We're getting almost 3.5 volts. So it looks like this right here is RMS. So we'll see what's going on our output. So I'm gonna take the oscilloscope probe and hook it up right here. And what we should see here is we should see it don't look like we got anything, does it? Let me take channel 1 and put it over there. We run out of disk space on that computer over there. You can only leave your simulation running so long. Guys, I don't know what's going on. Can y'all see anything I've done wrong? So here we have the positive going to here, because here we have the positive there. I can't figure out why we're getting a DC offset off of my function generator. I think I'm moving my meter lead around. And then electronic workbench just crashed. And we lost everything. Dang it. Don't you love technology? Huh? And I don't think I don't have that circuit chain saved. This is the two power supply bias that you'll be doing in the lab. And you can see what we've done is when we go to these other bias methods, what have we done? We've dropped off one of our power supplies. See, y'all more than welcome to play around with this if you want to. What we can do is we got all the resistors. Is you can come up here and put a bar across it and then highlight everything, and then you hit Control R, and it rotates all of them together. And then we can come up here and spread around. And then we're going to connect these two resistors here together. And then we're going to come over here and get, here's our transistors. We're going to get a NPN transistor and put it right here. I'll try to put it right there. You get them too close together, a lot of times it won't let you connect them. So we okay. So here we're doing what we call a drag. Everybody's familiar with drag, right? And then come over here and get the base and drag it into this one, and it should automatically put our connection dot in there. Okay. And then we'll connect these two to common. And then we'll put a DC power supply right here. This says VCC, by the way, but this is a digital VCC, so that would be what, if you take digital, then that would be what we use for digital. And digital VCC is equal to 5 volts. In analog circuits or amplifier circuits, VCC can be any value. And then we're going to put a capacitor here. And we're going to turn it this way, or try to. We're going to make it 10 microfarad, right? And then we're going to take a capacitor. I'm going to save this when I get this drawn this time. And it's going to point that way. And we're going to make this 10 microfarads. And then we're going to put a load resistor out here. And we're gonna make this 1 mega ohm. Something just happened. Okay, so this is supposed to be what? This is supposed to be 20 volts. This right here is supposed to be 100K. This right here is supposed to be 10K. This is supposed to be 10K. And that's supposed to be 1K. And we need a meter. And we need a oscilloscope. Be almost as easy to hook the whole real circuit up, wouldn't it? Okay, everything look okay? 20 volts. Okay. So this is our input. Yeah, it's doing right now. This is, I thought it was. Might have to give up on this, guys, until I figure out what's going on. It started out working and then it just disappeared. Oh, Somehow I set my amplitude to 0 volts. Still. I guess we'll just have to wait for this to be another day. I wish we could have showed you that. The bias looks okay. Here's the DC voltmeter. But it's not, our oscilloscope's not showing anything in, it's anything out. Let me flip my meter over to AC. Yeah, something is freaking out. It's saying that I've got 7 volts AC coming out of this. And it says I've got 25 millivolts. So I don't know what's going on. So we'll see if we can figure that out. Like I said, I'm sorry. So what we should have seen, if we hook it up, we should have seen this voltage and this voltage would be what? It should have been 180 degrees out of phase. Y'all understand why? Because when the input goes positive, this base current goes up, this base voltage goes up, which causes this current to go up, which causes this transistor to saturate more. So what would be this one? What would this one be? This is a good example. Y'all calculate this. You know, do that. So what's the first thing we're going to calculate? What's the thing should we calculate? VB, VE, VC, and VCE. Those are the 3 voltages. Can y'all do that? Huh? Huh? Can y'all do it? It's that have nothing to do with each other. So over here on my left side, I've got this. This is R1 and this is R2. And what do I want to find? I want to find VR2. So VB is equal to VR2. Now over on this side, we're going to do this. Here's my transistor. I know the size of this resistor. I know the size of that resistor. I don't know the size of the unknown resistor, and it don't make any difference to me. What I do know is the voltage drop across this resistor right here, which we call VE. VE, and that's not going to be recorded. VE is equal to VB minus 0.7. So I know, so if I calculate this voltage right here, I know that voltage right there. If I know that voltage right there, and I know the size of that resistor, I can calculate my current. If I calculate that current, this is a series circuit, so that means I know the size of this resistor, I can calculate that voltage drop, right? You understand? So all this is just a 2 simple series circuits. The only thing I know is I calculate that, and that voltage right there is set at 0.7 of a volt less. So what are we looking for? We're looking for VB, VE, VC, and VCE. Now, VCE tells you the formula. VCE is going to be VC minus VE, according to Kirchhoff's law. Two resistors out here, the collector resistor and the emitter resistor being the same size. But this is good enough to try to solve for these four values right here, right? What's that? Is that right? Everybody get that? VE would be what? VC would be so VC means we're going to make our measurement right here. So the only difference between here and here, so if I measure right here, this would be VCC. If I measure right here, this is going to be VC. So the only difference between VCC and VC is the voltage drop across that resistor. So VC is going to be equal to VCC minus DC. Can y'all see that? But why can't you do that? Because you don't know the resistance of the transistor. But you do know the current flow here. You do know the current flow there, because that's a series circuit. If I knew that voltage drop, I could add this one plus that one, but the problem is I don't know R of the transistor. I do know that R, and I do know this R, and I do know the current flow. So if I know this R, I know the voltage drop there, I can calculate the current. If I can calculate the current, I can calculate the voltage drop across that resistor. Right? You understand? According to Kirchhoff's law, that all I need to do is to calculate this, is subtract what? Is subtract that. So what's VC? Anybody got it? What's that? Well, it's minus VRC. I'm sorry. I just didn't put it on there. So, but that's what I was saying. The only difference between VC and VCC is the voltage drop across RC. Right? You'll understand that. So VC is equal to VCC minus VRC. That's all it is. So what we got for VC? So VC would be equal to what? It's going to be equal to 30 volts minus, what's our current? 8.7 milliamp. So how much is this going to drop up here? 1 volt per milliamp. It's going to drop 8.7 volts, right? So what would VC be equal to? Okay, 11.3 volts. No, understand? Yes or no? Okay, what would VCE be? Well, VCE, it tells you what to do. So VCE is going to be equal to VC, which is 11.3, minus VE, which is 8.7. Right? 2.6. Is it in saturation, or is it cut off, or is it in the active region? It's active, but it's almost saturated. What we're shooting for is we're shooting for VC to be exactly 1/2 of that. And that's where we're trying to bias the amplifier. We want it to bias right in the center of ACC. That way we get as much positive out as we do negative. Well, we never get negative, but out, right? Understand what I'm saying? Yes or no? Yeah, so if I've got 30 volts out, that means the maximum I could possibly get out, and I'll never get that because of is 30 volts. The minimum I can get out is 0 volts. So what I would like to do is I would like to bias it right here at 15 volts. That way, when my output swings, it could swing up just as high as it does what? swings down. If it swings above here, then the transistor cuts off. We can't get more than 30 volts out. If it swings down here and goes past zero, we can't get past zero, so because the transistor is saturated, right? You understand that? Of course, we'll never get zero because of that resistor right there, but we would like to put it in the center. And what sets it, of course, is the size of these resistors right here. So with a VCC equal to 2.6 volts, this guy is operating towards saturation, which means the output signal would clip down here before the input signal clips up. But we are in the active region, barely. So it didn't take me long at all to hook this little circuit up. I should have done this first. And then we'll. The problem is that I'll have to. What I'll do next class, I'll come up here. I'll leave the circuit up. The problem is that we can't get this thing down below 2 volts. So what I'll do next class is I'll get a pot so we can get this down to our calculator. So this is my input right here. So here's my transistor, and it's a 3904. 3904 goes emitters to the left, and the base is in the center, collector. So here's my 100K hooked up to power. Here's my 10K, and it's connected to the base. Here's the 1K. It's connected to my emitter. Here, this is my common of my circuit right here. This is DCC up here. So we have two resistors connected up to DCC, right? So we have a 100K and a 10K. So here's my 100K. Here's my 10K. They're connected together. Then over here, connected to VCC, I have a 10K and a transistor and a 1K. So here's my 10K. Here's my transistor. So this is connected to the collector. This is connected to the emitter. Here's my input capacitor right here. It's connected to the center of these two resistors. Even if these resistors over here, remember that's common through there, right? Here's my output. Here's my output over here. So when I hook up my scope right here, this is my input coming in. When I move it over here, this is the same input, but now it's riding up on top of DC, right? So that's what the capacitor does. It lets the input come in, and I'm overdriving the transistor because we're on this original circuit. So we're supposed to be setting at 2 volts, and if I put 2 volts in, then it's going to cut it off and saturate it. So we'll look at this later on and show you what's going on. But this is the output. And notice this riding should settle down. Oh, I don't have a load gain, guys. I don't have a big resistor for a load. The capacitor has nothing to discharge through. There's a 10K right there. What's the color code? 100K, I'm sorry. Yeah, brown back yellow. So it's very common when people do that to think zero is a zero. So a lot of people just say, what's the color code for 100 ohm? And they'll say brown, black, black, because they see zero as the zero. But remember that last number is how many zeros you add, right? So if I want 1 0, then it's brown, black, brown, which would be 100 ohms, right? And that people get that every time. I could put that on the test. What would be a color code for a 100 ohm resistor? And somebody in this class is going to put brown, black, black. So it should discharge now. So let's see. And we're still not getting the gain that we're supposed to get. In fact, it stopped working altogether. Oh, my. So this is what's up neat over here. I have AC change in DC, right? And I move over here on the other side of the capacitor, and I get nothing. Oh, dang, sorry. These leads on these, the leads on those transistors are very small, so it pulled out. So over here we have AC riding on top of DC. Somewhat told us. So right here we have AC riding on DC, right? And then I go on the other side of that capacitor and we get AC. Can you see how the DC is blocked by the capacitor? And what I'll do next class, I know it's time to go. What I'll do next time is, the problem is that I can't turn this down far enough because of the gain of the amplifier. So what I'll use a pot so we can get the voltage we want to on this thing, so we can actually see the gain. Are we okay? And I don't have 20 volts either, so that would be my problem. Let's see if that helps a little bit. Yeah, it helps a lot. So here's my input. Here's my input. Right. Here's my output. Input. Output. So it is what was happening is I had my power supply turned down so much. So look, so we're using, how did we calculate that? Nothing but Ohm's law. But now we've got a device that gives us gain. So we're getting more out than we're doing what? This is what we're putting in. This is what we're getting out. Now we'll hook up the 2 scope probes next class, and you can see they're 180 degrees out of phase. But and that's transistors. Now we're going to keep adding to this, which is so neat, and we're going to bump this gain up to about 80 or 100. VCC, yeah, so V collector to emitter. So that means I take my voltage on my collector. VC is measured right here. So the only difference between VC and that right there is the voltage drop across RC. So that means VC is going to be equal to VCC minus VRC. Kirchhoff's law. Kirchhoff's law. Voltage drop. Okay. I didn't come up with anything. No, that's not. That's for the other circuit. We'll go back and look at that. Yeah. Minus 8.7. Yeah, that sounds. Yeah, like I said on that one, I didn't screw up like I did on the 110K that Taru caught for us, but